Welcome to the Deep Dive. We're tackling a fascinating puzzle today: how to reliably find anomalies in incredibly detailed medical images. Think about the richness of information in, say, a breast tomosynthesis scan or a high-resolution chest X-ray data that's absolutely vital for accurate diagnoses.
Right. And the inherent challenge is that if image resolution increases, so does the complexity for these anomaly detection systems. It becomes exponentially harder, really, to
Yeah.
distinguish between normal variations and actual abnormalities.
Exactly. And for years, the go-to fix has been to, well, shrink these massive images down, often to something like 256 by 256 pixels.
Which seems tiny compared to the original.
It is, but the big problem there, as any doctor would tell you, is that you're throwing away potentially critical fine details. It's a necessary compromise for the existing tech, maybe, but far from ideal for clinical practice, where, every pixel can matter. So a major takeaway right off the bat is that we've been forced to lose information to even attempt this task.
That's precisely why we're focusing on a new approach called SWSSL. That's SWSSL, which stands for Sliding Window-Based Self-Supervised Learning. This method is designed to directly handle those high-resolution images in their full glory without any need for downsampling.
Okay, let's unpack this. Sliding window. So instead of looking at the whole massive image at once, SWSSL examines it in smaller chunks, right? Like moving a magnifying glass across the image and analyzing each section or patch individually.
That's a great analogy, yeah. Think of it like trying to understand a giant mural. Instead of stepping way back and losing the fine details, you move closer and examine each tile, sort of individually, to grasp the overall picture. SWSSL does pretty much the same with image patches.
Makes sense. But processing all those individual patches sounds like it could introduce new difficulties. How does the system keep a sense of the overall image? Doesn't it risk getting lost in the details of each tiny piece? Wouldn't there be a lot of variance between these small patches?
You've highlighted two key challenges there. When you're dealing with individual, potentially slightly misaligned patches, it's definitely harder for the network to learn the consistent structure of a normal, healthy image.
Uh-huh.
Plus, the visual features within each small patch can vary quite significantly depending on where in the image it's taken. SWSSL addresses this by learning features that remain stable, consistent, even when the image undergoes certain transformations. And that's where self-supervised learning comes into play.
Self-supervised learning. So the network teaches itself what's normal by looking at lots and lots of normal images without needing us to specifically label any anomalies. It's learning the rules of normal on its own.
Exactly. The network learns to identify recurring patterns and consistencies in healthy images. A crucial aspect of this is teaching the network to recognize features that are invariant to certain changes in the image, things we call augmentations. Think of it as learning to recognize your friend, even if they change their hairstyle or, I don't know, wear different glasses.
Okay, augmentations. This is where it gets really interesting, I think. We're talking about things like rotating, cropping, or maybe changing the brightness of an image, right? Standard ways to help a network learn more effectively.
Yeah, the usual toolkit.
But I remember reading that some of these common techniques can actually be harmful in medical imaging. Is that right?
That's a critical point, yes.
Yeah.
The researchers behind SWSSL discovered that a very common augmentation in general computer vision, taking a smaller part of the image and then stretching it back to a standard size, that sort of thing can actually be detrimental in medical imaging.
Why? Why would that hurt?
Well, because resizing can distort the crucial pixel densities, which can be a key indicator of disease. Imagine zooming way in on a tiny, subtle shadow. You might change its apparent darkness, its density, and potentially misinterpret it. So a major insight here is that what works for, say, CAD photos can actually hurt in medical imaging because we lose crucial density information by resizing.
Wow, okay, that makes perfect sense when you put it like that. So if resizing is bad, what kind of augmentations do work well for medical images? I recall something about flipping the image's colors, inverting the pixel intensities being surprisingly helpful.
You're right on. Inverting the pixel intensities can be surprisingly beneficial. For example, in chest X-rays, this can make the normally bright bones appear dark, which can help the network to better focus on subtle abnormalities in the lung tissue.
Okay.
Similarly, in breast tomosynthesis, it can help highlight minute density changes associated with lesions. It's not just about seeing bones better, though. It forces the network to learn about the relationships between light and dark areas, representing different tissue densities in a more fundamental way, rather than just memorizing what normal bright bones look like, if that makes sense.
That's counterintuitive, but brilliant. Now, you also mentioned something about learning from adjacent patches earlier. If we're not using cropping and resizing to get those overlapping views, how does SWSSL encourage the network to understand the relationship between nearby parts of the image? How does it connect the dots?
Good question. That's addressed with a new component called continuity preserving loss, or CP loss. The fundamental idea is to encourage the network to represent patches that are physically close together in the original image in a similar way within its learned feature space.
Okay.
Think of it like ensuring that words used to describe neighboring parts of that mural we talked about have related meanings.
So if two patches are right next to each other in the scan, maybe overlapping a bit, their internal descriptions within the network should also be similar in some way.
Precisely. This helps the network maintain a sense of the spatial context that might otherwise be lost when you're just processing individual patches in isolation.
And all of this together, the sliding window, the smart augmentations, the CP loss, it leads to some really significant improvements in performance, right? I saw some numbers, I think, about notable gains on those breast tomosynthesis and chest X-ray data sets.
Absolutely. SWSSL achieved an impressive 8.03% improvement in AUC, that's area under the curve, a key metric for measuring how well a model distinguishes between, normal and anomalous cases on breast tomosynthesis.
Wow, 8%.
Yeah, and a 5.66% improvement on chest X-rays compared to existing leading techniques. These are substantial gains, really suggesting a real step forward in accurately detecting anomalies in these high-resolution scans.
And practically speaking.
Well, practically, an improvement like that could lead to fewer misdiagnoses and potentially earlier detection of critical conditions. It's a big deal.
So the goal for this deep dive is clear, to really grasp how SWSSL achieves these results. How does processing these small pieces at high resolution, combined with these carefully chosen augmentations and this continuity-preserving loss, lead to such a significant boost in anomaly detection? Let's maybe start by revisiting why those low-resolution images are such a limitation in the first place.
Well, as we touched on earlier, the ability to make an accurate diagnosis in many medical imaging modalities, especially high-resolution ones like breast tomography and X-rays, often relies on identifying very, very fine details.
Right, the subtle stuff.
Exactly. These could be subtle changes in texture, the precise shape of a tiny structure, or minute variations in tissue density. When you drastically reduce the resolution of an image, you inevitably lose some of this crucial information. It's like trying to read a book by only looking at every other word, maybe.
So a tiny but suspicious cluster of microcalcifications in a breast scan might just become a blurry, indistinguishable spot at a lower resolution.
Exactly that. And it's not just about losing details. Trying to train anomaly detection models directly on the full high-resolution images presents a huge computational challenge. The difficulty of training roughly increases by the square of the input size.
Whoa.
So if you double the resolution in both height and width, you're looking at something like a four-fold increase in the computational power needed. It gets out of hand quickly.
That's a massive jump in resources. So the computational cost becomes a major barrier for standard approaches then.
Precisely. And simply trying to make a low-resolution trained network work on high-resolution images by just adding more layers to upscale the output, well, that often leads to unstable training and can produce nonsensical results.
Because it's guessing.
Pretty much. The network hasn't actually learned the fine-grained patterns. It's just trying to invent details it never truly saw during training. It's not reliable.
Okay, so we're in this difficult position where we either lose critical information with low-res images or face these insurmountable computational costs with high-res data. This brings us back nicely to the sliding window approach. Can you explain in a bit more detail exactly how that algorithm works within the SWSSL framework?
Certainly. So imagine your high-resolution medical image. The sliding window algorithm picks a smaller rectangular window, a patch of a specific size, say 256 by 256 pixels maybe, and systematically moves it across the entire image, both horizontally and vertically.
Okay, step by step.
Right, it moves by a set number of pixels at each step that's called the stride. This process effectively divides the large high-resolution image into a collection of smaller, often overlapping patches. The paper actually has a good figure illustrating this difference between the traditional low-res method and the SWSSL approach.
So instead of feeding one single downsized image into the network, we're feeding a whole sequence of these smaller but still high-resolution patches.
Correct. The neural network then processes each of these patches individually. During the testing phase, when we want to determine if a new high-res image contains an anomaly, We again use the sliding window to extract all the patches, feed each one through the trained network, and then combine the results from all the patches somehow to make an overall decision about the entire image.
And because these patches are processed one at a time, the underlying network structure doesn't need to be fundamentally different to handle the higher resolution of the original image. It's just dealing with smaller pieces that happen to have that original level of detail.
Exactly. It's a clever way to utilize the existing network's capacity to analyze high-resolution information without that massive increase in computational demands for each individual patch processed. However, as we discussed earlier, dealing with these diverse and potentially misaligned patches introduces a new level of complexity to the learning task itself.
Which leads us directly to the self-supervised learning aspect. Why is this so essential for handling the increased variability of these individual patches?
Well, because we're no longer feeding the network consistently sized and aligned whole images, right? Individual patches can capture vastly different parts of the anatomy, and their original spatial relationship within the larger image might not be immediately obvious to the network when it's only seeing them in isolation.
Makes sense.
So, self-supervised learning provides a powerful way for the network to learn meaningful representations from a large number of unlabeled but normal patches. The core objective here, as we said, is to learn features that remain consistent even when the same patch is viewed under different conditions, that is, after undergoing augmentations.
So if we take one specific patch and create two slightly different versions of it through augmentation, the goal of self-supervised learning is for the network to recognize that these are still fundamentally the same underlying piece of information. It should see past the superficial changes.
Precisely. And the SWSL's method specifically employs a self-supervised learning technique called Barlow twins loss. What's particularly ingenious about this is how it measures the similarity between the learned features of two different distorted views of the same image patch. Instead of traditional comparison methods, it looks at the cross-correlation of these features across a whole batch of training examples.
Okay, cross-correlation across the batch.
Yeah. Essentially, it encourages the network to make the representations of the two augmented views similar to each other within that batch, while simultaneously minimizing the redundancy between the different features the network learns. The goal isn't just similarity, it's learning truly diverse and informative features.
So it's not just about making the two versions look alike to the network, but also ensuring that the network isn't learning the exact same thing in multiple ways in its internal representation. It's pushing for a more efficient and diverse understanding.
That's a great way to put it, yeah. It encourages the network to develop a rich and varied set of features that are robust to the applied augmentations. Now, when it comes to actually detecting anomalies during inference, the process involves first creating a memory bank of the features extracted from all the normal training image patches.
So we take all those normal training patches, run them through the trained network, and store their learned feature representations. It's like building up a library of what normal looks like in this feature space.
Exactly. Then, when we have a new image that we want to test for anomalies, we again extract patches using the sliding window and get their feature representations using the trained network. Now, for each individual neuron in the network's output layer, we compare its activation on the test patch to the activations of the same neuron across all the stored training patches that came from the same relative location in the image.
Okay, location matters.
Yes. The anomaly score for that specific neuron is then determined by how different the test activation is from the most similar activation in our normal memory bank for that location. Finally, the overall anomaly score for the entire test image is the highest of these neuron-level anomaly scores found across all patches and all neurons.
So a single, highly unusual activation of one specific neuron in any of the process patches can trigger a high anomaly score for the entire image. It's looking for the most out-of-place feature anywhere.
That's the core idea. If any part of the test image generates a feature representation that is significantly different from anything the network has learned from normal data at that location, it will likely result in a high anomaly score for at least one of the neurons.
Now let's circle back to the vital role of augmentations. We've established why resizing can be harmful. What specifically makes this inverting operation so beneficial in this context of self-supervised learning for medical images?
As we mentioned, inverting the pixel intensities essentially flips the contrast of the image. White becomes black, black becomes white. For medical images, this seemingly simple operation can have a profound impact on what the network prioritizes learning.
How so?
For instance, in a standard X-ray, bones appear bright. Inverting the image makes them dark, which can then help the network to better identify subtle changes or abnormalities in the normally darker soft tissues, like the lungs. The key finding, as shown in the research, is that the common practice in general image processing of cropping a region and then resizing it, a technique often used to create both broad and zoomed-in views, actually hinders performance here because of that resizing issue we discussed.
Right, the density distortion.
Exactly. So by inverting, we're essentially forcing the network to learn features that are not solely reliant on the absolute brightness or darkness of pixels. It has to look beyond just light and dark at the structure.
Precisely. It pushes the network to learn based on the underlying structural relationships and the patterns formed by different tissue densities, rather than just memorizing what normal overall brightness levels look like. This makes the learned features more robust to variations in how the images are acquired and can highlight subtle anomalies that might be masked by overall intensity differences. And since getting rid of that cropping then resizing step means we lose a natural way to get information from adjacent parts of the image, that's where the continuity preserving loss comes in to fill that gap, right? How does that work again as a substitute to ensure the network understands the spatial relationships between patches?
Exactly. The CP loss is specifically designed to encourage the network to encode patches that are spatially close to each other in the original high-res image in a similar region of its learned feature space. The underlying principle is that if two patches are neighbors or significantly overlap, their learned representation should also exhibit a high degree of similarity.
Makes intuitive sense.
The loss function achieves this by measuring the difference between the cosine similarity of the feature representations of neighboring patches and a target similarity score that is directly calculated based on the actual amount of overlap between those two patches.
So if two patches have a large overlapping area, their learned features should be highly similar, reflecting that overlap in the original image. The target score is higher.
Yes, the target similarity score is higher for patches with greater overlap. The CP loss then penalizes the network if the similarity of their learned representations deviates significantly from this target. This encourages the encoding function to be continuous, meaning that small shifts in the input image, like moving from one patch to an adjacent one, should result in proportionally small shifts in the learned feature space. It helps the network understand that these neighboring patches aren't independent entities, but are part of a larger continuous structure.
Okay. And I think you mentioned it also applies to different versions of the same patch.
That's right. The CP loss is also extended to consider different augmentations of the same patch. In that case, the target similarity is simply set to 1, because it's fundamentally the same underlying patch, just viewed under different augmented conditions. This reinforces the core idea of the self-supervised learning objective, ensuring that different views of the same input have similar representations.
And the final training uses both losses.
Correct. The overall training process uses a combined loss function that incorporates both the Bartlett twins loss and this continuity preserving loss. They work together.
So we've got this elegant system, the sliding window for high-res data, self-supervised learning with Barlow twins, and these carefully chosen augmentations like inversion to learn robust features, and the CP loss to maintain spatial context. Now let's look at how well this all comes together in practice. What kind of data did the researchers use to validate the effectiveness of SWSSL?
They utilized two well-established publicly available datasets, breast tomosynthesis, or DBT, and chest X-ray. These are valuable because they represent different medical imaging techniques and, importantly, different types of anomalies that need to be detected.
Right, DBT is more 3D-like.
Sort of, yeah. It creates the 3D-like reconstruction of the breast, and the anomalies of interest are typically masses or distortions in the tissue architecture. The chest X-ray dataset consists of standard 2D X-ray images, with the primary anomaly being pneumonia. The research paper gives the specifics on the number of patients and images used for both training and testing for each dataset.
And what were the key performance metrics they focused on to evaluate how well SWSL was performing? How did they measure success?
They use the standard evaluation metrics commonly employed in this kind of anomaly detection research, so things like AUC, which we mentioned, area under the curve.
And how well it separates normal from abnormal.
Exactly. Also the F1 score, which balances precision and recall, overall accuracy, sensitivity, that's the rate of correctly identifying anomalies, the true positive rate, and specificity, which is the rate of correctly identifying normal cases, the true negative rate.
And the results, as we hinted at earlier, were quite compelling. Can you highlight the main performance improvements that SWSSL demonstrated compared to other state-of-the-art methods in this area?
Absolutely. Looking at the results tables in the research, SWSSL consistently outperformed a variety of existing cutting-edge methods on both of these challenging datasets. On the breast tomosynthesis dataset, it achieved that AUC of 0.7848, which was a significant 8.03% improvement over the next best performing method.
That's substantial.
It really is. For the chest X-ray dataset, the AUC reached 0.8877, representing a substantial 5.66% increase over the runner-up. What's particularly noteworthy, I think, is that the researchers also experimented with simply applying the sliding window technique to some of the existing reconstruction-based anomaly detection methods.
Just using the window part?
Right? Just applying the windowing, but keeping the old learning method. And this didn't lead to significant improvements, and in some cases, it even negatively impacted performance. This strongly suggests that it's not just about processing high-res patches. The specific self-supervised learning approach and the unique design of SWSSL, including the CP loss and augmentations, are critical to its success.
That's a really important point. So just feeding high-res chunks to a standard anomaly detection algorithm isn't the magic bullet. It's the whole SWSSL package, the way it learns from these patches, that makes the difference. I also noticed in the results that SWSSL achieved a very strong F1 score in accuracy on the DBT dataset, even with a slightly lower sensitivity compared to a couple of other methods, but a notably higher specificity. Why is that trade-off potentially beneficial in a clinical setting?
That's a crucial consideration in medical diagnosis, absolutely.
Mhm.
High specificity means fewer false positives, fewer instances where a healthy patient is incorrectly flagged as potentially having an anomaly.
You were scared.
Exactly. This is incredibly important because it reduces the burden on the healthcare system by minimizing unnecessary follow-up procedures, biopsies, extra scans, and all the associated anxiety for patients. While high sensitivity is also vital, of course, to avoid missing true cases of disease, a higher specificity can be particularly valuable in screening programs, where the goal is to efficiently identify individuals who truly need further investigation without overwhelming the system with false alarms.
And they could adjust it if needed.
Right. The researchers mentioned that by adjusting the decision threshold, they could actually achieve 100% sensitivity with a still reasonable specificity, if that were the priority in a specific clinical application. And looking at the examples in the paper, some of those DBT anomalies are incredibly subtle. It really highlights the difficulty.
It's great to see these quantitative improvements, but it's equally important to understand why SWSSL is so effective. That's where the ablation studies come in, right? Taking components away to see their impact. Let's start by looking at how the different choices of augmentations impacted the results.
Yeah, those ablation studies are really revealing. They're detailed in the research, showing the step-by-step impact of various augmentation strategies on both the DBT and chest X-ray datasets. So by comparing the baseline Barlow twins model, which still used that problematic cropping then resizing augmentation,
The standard way.
with the sliding window model that removed resizing, they clearly demonstrated an improvement in AUC on both datasets simply by eliminating that detrimental operation. This really underscores the negative impact of resizing on this type of medical image analysis.
Just taking it out helped.
It did. Then, by adding the inverting operation to one of the augmented views of the patch, they observed a further increase in AUC on both datasets. This confirms its value in encouraging the network to learn more fundamental structural features rather than just relying on pixel intensity.
And finally, the CP loss.
Finally, the addition of the continuity-preserving loss on top of the sliding window approach and the inverting augmentation provided yet another boost in performance, particularly noticeable on the chest X-ray dataset. It suggests that learning the relationships between neighboring patches contributes significantly to a more comprehensive understanding, especially maybe when anomalies involve larger areas or context.
It's fascinating to see how each of these components individually contributes to the overall success, like building blocks. The researchers also explored different ways of implementing that continuity-preserving objective, didn't they? Different formulas for it.
Yes, they conducted further experiments, specifically on the DBT dataset, to evaluate different formulations of the CP loss. They compared their final approach with alternative methods, like focusing solely on similarity along the batch dimension, or only considering adjacent patches without weighting by overlap, or even just looking at different augmentations of the same patch again, but through the CP lens.
And their chosen method worked best.
By far. The results clearly indicated that their chosen formulation, which uses the cosine similarity between the unnormalized feature representations and a target similarity based on the actual overlap between patches, yielded the best performance. The other variations either hindered performance or just didn't provide the same level of benefit, highlighting the importance of considering both the relationship between spatially close patches and their actual degree of overlap.
And one final aspect of the ablation studies I wanted to touch on was the evaluation metric itself. SWSSL uses this slightly different approach to calculating the anomaly score at the neuron level, not the patch level. Why is that significant?
Right. The research highlights that their proposed neuron-level evaluation strategy led to better performance compared to a more conventional patch-level evaluation, where you might average scores across a patch or take the max patch score.
Why does neuron level work better here?
Well, their analysis of the distribution of neuron anomaly scores showed that many neurons tend to have low scores, likely capturing common features present in both normal and potentially abnormal images, background texture, general anatomy, that sort of thing.
Yeah.
By using the maximum neuron score across all patches and all neurons as the overall image anomaly score, SWSSL effectively focuses on the neurons that exhibit the most unusual activations for their specific location.
Okay.
It thereby mitigates the noise from neurons that are simply detecting general image characteristics. It's like focusing on the single loudest alarm bell, rather than trying to average the sound of all the sensors, some of which might just be picking up background noise.
So it's honing in on the most outlying features detected by the network anywhere in the image, rather than averaging across all features, which could potentially dilute the signal of a true, perhaps localized anomaly.
Precisely. It makes the detection more sensitive to those critical, highly divergent features.
And to really demonstrate the robustness and broader applicability of SWSSL, the researchers also tested it on a completely different type of medical imaging data, right? Something other than X-rays or tomo.
Yes, and this is a strong indicator of its generalizability. They applied SWSSL to an optical coherence tomography OCT dataset. This is an entirely different imaging modality used to visualize the layers of the retina in the eye, often in very high resolution.
But how did it do?
Even on this new type of high-resolution data, SWSSL achieves state-of-the-art results, significantly outperforming the previous best method for anomaly detection on that specific OCT dataset. This suggests that the core principles behind SWSSL, effectively handling high resolution through a sliding window, carefully selecting augmentations appropriate for medical images, and preserving spatial continuity, are not limited to just breast tomosynthesis and chest X-rays, but have broader applicability in the field of high-resolution medical image anomaly detection across various imaging modalities.
Okay, let's try and summarize the key innovations of SWSSL then. It effectively tackles the challenge of finding anomalies in high-res medical images by processing them in smaller patches using a sliding window, thus avoiding that crucial information loss associated with downsampling.
Check.
It's really remarkable how they've shown that common data augmentation practices from general computer vision, especially resizing, can actually be detrimental in this specialized field.
A really key finding.
Instead, they've demonstrated the advantages of augmentations like inverting pixel intensities, which guides the network to focus on critical structural information. And the introduction of the continuity preserving loss is a clever way to maintain the spatial relationships between these individual patches.
Exactly. The significance of these findings is that SWSSL presents a very promising pathway towards achieving more accurate and reliable anomaly detection by fully leveraging the rich detail present in high-resolution medical scans. And this has the potential, down the line, to lead to earlier and more accurate diagnoses, ultimately contributing to improved patient outcomes.
It really highlights how crucial domain-specific knowledge is when applying these advanced machine learning techniques, doesn't it? What works well in one area, like general image recognition, doesn't always translate directly to specialized fields like medical imaging, where the fundamental properties of the data, like pixel density, are so unique and clinically significant.
Absolutely.
The success of SWSSL in focusing on structure through inversion and spatial relationships through the CP loss underscores the need for these more nuanced and tailored approaches.
This research also raises several intriguing questions for the future, too. For instance, are there even more effective, self-supervised learning objectives that could be specifically designed for the task of anomaly detection in medical images? Maybe something beyond Barlow twins or SimCLR.
Good point.
And how can we further optimize the computational efficiency of processing so many patches during inference? That's still a hurdle, making these powerful methods more practical for widespread clinical adoption. These are exciting areas for ongoing research and development, for sure.
It definitely makes you wonder about other fields beyond medical imaging, where high-resolution data and the detection of subtle anomalies are critical. Could similar patch-based, self-supervised approaches, combined with carefully considered, domain-aware augmentation strategies, could they be beneficial in areas like analyzing detailed satellite imagery, maybe, or perhaps in detecting microscopic defects in high-precision manufacturing
Well, it
processes?
seems very plausible. The core ideas might transfer quite well.
It's a really compelling direction of research. Thanks so much for taking this deep dive with us today and illuminating this fascinating work.
My pleasure. It's really exciting stuff.